Hello everyone. So we'll continue the frequency response of 5 transistor OTA structure. We have seen in the previous videos on top level how to calculate the pole, how to calculate this transfer function and write its pole zeros and whatever possible UGB as well. Okay. So in this video we'll extend this concept uh, to some more depth. Okay. So again, I'll start what the transfer function we have written. If there is a pole and zero, and then what we can write, any transfer function can be written as a DC gain 1 plus Sy omega z. If this pole is zero, is a left hand side zero, 1 plus Sy omega p1, which is usually I consider the dominant pole, 1 plus omega P2 we consider the non-dominant pole. Okay, so this is the general transfer function where A naught is a DC gain, omega g is a zero frequency, omega P1 is a dominant pole frequency, and omega P2 is a non-dominant pole frequency. Okay, so what in general what we consider that this omega P1 is much lesser than this omega P2, is also we say omega P1 is much lesser than omega UGB. Also, for the better design or the first order design, we consider this omega p1 is much lesser than this omega g. In general, we have considered these the three things. Okay, so okay, we have seen how to calculate the zero, how to calculate the pole. So before going much into the depth or on the transistor level, I'll take little more things on the top level design. Okay, so yesterday what we have seen the zero calculation. So I'll take few more circuits for zero calculation so that you can have the better idea. Zero calculations. Okay. So what are the things? Okay, the cases when there are two current paths from input to output, input to output, then there is possibility of zero. Why I told possibility, you will see this thing soon. There is possibility of zero. Okay, second thing, the sum of voltages is giving you the output voltage. What it means, let me see. Output voltage. So what we are trying to make here, the point is, in general, when we write the transfer function, what we write, V out of S divided by V in of S. Okay. So for zero calculation, what should be there? For zero, your transfer function should be zero. And for that, what we assume, our V out of S should be zero. And for pole, what we consider, for pole calculation, what we consider, h of s should be infinite. And for that sense, what we see, your v out of s should be infinite. Okay, for given v in, for given v in, but for this analysis, we make v in to be shorted. Okay, so we'll explore this concept in few more circuits, then we'll coming back to the then we'll come back to the 5 transistor OTA structure. Okay, so what does mean that there is a possibility of zero when there are two current paths? What the mean? Okay, so the motivation is for calculation of zero, what we see v out equal to zero, that's it. Okay, so if this is my input, let's say this is my input and I have two paths. Let's say this is a one path, which is a Z1, and this is a second path, it is a Z2. and these two paths are giving me the output voltage Vout for some load which I don't care, ZL. Okay. So what is the way of calculating it? So this is my first current path, this is my second current path from input to output. Okay. So what is the current? So first thing is what? We have to keep this output zero. So what extra we can do here? For making the output zero, we can simply short the output. If we will short the output, this ZL will not be visible. Okay. So what do you do? While we short this output, simply ZL will not be effective. So I'll remove the ZL. This is my I should say out, and it should be equal to 0 for giving me the 0. Okay. So this is my I2, this is my I1, this is my Z1, this is Z2. Okay. So what is I1? I1 is my V in Y Z1, and what is I2? I2 is my V in Y Z2. So what is I? I is I1 plus I2, and it should equal to 0. So from here we can see Z1 plus Z2 should equal to 0. Yes. Okay. So it means your Z1 should equal to minus of Z2. So what we are seeing here, the one impedance should be negative of other. Negative of other. So what we can conclude from here, the conclusion is two resistors two resistors can't follow this above requirement, can't follow this above requirement, because we know that two resistance cannot be like this. So resistances are some positive quantities, so we cannot say one resistor is the negative of other. So what is the point here? Point is there that either one of the Z1 or Z2 should be a reactive quantity. Reactive quantity. Okay. So both cannot be resistive quantity, or I will say both cannot be resistive quantities, because we know that two resistors cannot be like this. R1 is equal to negative of R2. Okay. So what I told, let's say if Z1 is your nothing but say R, and Z2 is nothing but say some capacitive element, so it is 1 upon Cs. Then there is a possibility that Z1 can be minus of Z2. For that, what is this? R equal to minus of 1 upon Cs. So S equal to minus 1 upon RC is your zero location. Zero location. So minus sign indicates zero location. Negative sign indicates left hand side zero, LHS zero. Okay. So we'll come what is the advantage and disadvantage of LHS or RHS zeros. We'll see it. Okay. Yeah. So this is the point. So yeah, pole frequency will be what? Sorry, zero frequency. So this is the location. Now zero frequency, if I want, then I'll take this magnitude only. So what is the zero frequency? I call it omega z, which is nothing but 1 upon RC. Okay. So this is a possibility. Either the way it's possible that if your Z1 is some resistive quantity or some reactive quantity, and your Z2 is a resistive quantity, then also it is possible. Okay. So if your Z1 is reactive, wait. So this is also possible when Z1 is reactive and Z2 is resistive. Z1 is reactive and Z2 is some resistive. So both the way is this possible. Now is it possible this Z1 is also resistive? Sorry, not resistive, reactive, and Z2 is also reactive. Is it possible? So both the reactive means if I take let both capacitors and here some load which is of no significance because output is considered as a short. This I call C1, this I call C2. So overall current I should be 0 for shorted output. Okay. So there are two ways of current. I equal to 0 means what are the I's? So one is V in C1s plus second current is V in C2s. So both are the reactive elements, capacitance. So is there 0 possible? So we'll see S equal to 0 is the 0. Why it happened? Because we have two paths visible, but what we see effectively there is a one capacitance only. The C equivalent is nothing but C1 plus C2, and for this case only, when we see that this is ZL, when we see at output, when the output will be 0 for this case when a frequency that is 0, it means this capacitor is open circuit, so input is not connected to the output. In that case there is a 0 current flow, so your output is 0. So this is also a 0. S equal to 0 is also place of 0. So there are two ways we have seen for calculating zeros. One way of sum of current from input to output is 0. This is a one way. Okay. So I mean to say one current should be out of phase of other, only possible when at least one element is a reactive element. Okay. The second thing what we have seen, if there is a only reactive element and at s equal to 0, this is open, means this case is only possible for an only reactive or more like a capacitive element between input and output. So what you can see, you can see this path is open. So this is the discussion of this particular point. Now the second point comes when there is a output is there, sum of the voltages, then there is also possibility of zero. Okay, so what this point is, let's say this is my circuit, this is some Z1 and this is the Z2 and this is the Z3. It is the output. Why I'm spending this much time on zero calculation? Because in this 5 transistor OTA, when we'll calculate the zero, we'll follow one of this way. What we have ways we are discussing. Okay. So another way of calculating zeros, because my ultimate motive is to make our output zero. This is my ultimate motive. What I will do, there is a the output is nothing but a sum of two voltages, what I call V3 and V2. Okay. So instead of saying V1 and V2, I will say okay, I will say V2 and V3. So overall, the output is sum of two voltages, V2 and V3. So my output is sum of two voltages, which here are V2 and V3. If they are equal, the only possible thing is there V2 should be out of phase of V3. Okay. So again, point comes if both the elements G2 and G3, if G2 and G3 both are resistive, let's say both are resistive. So is it possible that the sum of the voltages across these two elements is zero so that your output can be zero? Is it possible? Let's say Z2 is nothing but R2 for time being and Z3 is nothing but R3. So if some sort of current is flowing through these elements, I call this is R3, this is R2, and this is my way out. Okay. So, if some current is flowing, whatever the direction of current is, what is their output? Output is nothing but this current times because they are the series elements R2 plus R3. So is it possible that again they can be 0? No, this is condition. So this condition is not valid for two resistive elements. So again we can see if this is the condition for calculating the output voltage. Okay, so what I will say, yes. So if this is the condition, then my output is the sum of two voltages, which is only possible when the load side we have two means reactive, or I will say two means impedances there in this way. In this fashion, if there are two impedances, then what we can see, my output is sum of two voltages, as we can see here, V2 and V3. So if my target is to make the output zero, because the condition for zero is this only. So if V out equal to V2 plus V3 equal to 0, then V2 should be minus of V3. Let I consider here these two elements are resistive elements. So is it possible for the two resistive elements to make the output 0? No. Whatever the current direction is there, whether it is downward or upward, because the direction means the current through both these resistors are same, so it cannot be 0. For that, this condition should be matched, R2 equal to minus of R3. So overall, I'll say this thing is not possible with two resistive elements. What we have discussed for the case when two parallel currents are added, then also we cannot use two resistor elements. Okay. So what we have seen here, the condition comes out is that both elements cannot be resistive. Both elements cannot be resistive. Okay. At least, at least one should be reactive. So for the reactive, I am using the capacitance here. Okay. So let this is my Z2, this is my Z3, and here I am taking this output, and this is a circuit of the input side. This is my gain, and my target is to make the output 0. And what I am seeing here, this is my V2 and this is my V3, and some sort of current is flowing across them. Then for this output to be 0, what should be the condition? Z2 should equal to minus of Z3. Let Z2 is your resistor and Z3 is your capacitor, then it is 1 upon Cs. So what we can see, R is equal to minus 1 upon Cs. So again we can see S equal to minus 1 upon RC is the location of 0. Negative sign indicates this left hand side 0, and the frequency of 0 is again the 1 upon RC. Okay, so there is also possibility of 0 when there is a means impedance combination on the load side as well. Okay, yeah. So now this thing is done. So now we will come to this some higher order means transfer functions. Then we will see how to calculate the phase margin and what is the contribution of right hand zero to the phase margin. Okay, so now again come to the transfer function of any OTA structure, which is a naught 1 plus sy omega z 1 plus sy omega p1 1 plus sy omega p2. Okay, so usually we have seen in the GM cell only one pole is visible, no other thing is there, but where this zero and poles are coming, we'll see it. Okay, so yeah, so this is my input voltage. One more confusion that people can have, I will remove it. Okay, this is CL. Okay, so ideally what we have seen here, when there is a no load or no output impedance of GM cell was considered, then our transfer function was what? GM by CLS. Okay, and when load was considered, this pole shifts away from this origin, the dominant pole, and it comes at some frequency which we call. So this is the load that I want to drive, and this is the inherent property Yes, R naught is there as the output impedance of the GM cell. Then what transfer function we have seen? We have seen V out by V in equal to GM by G naught divided by 1 plus CLS by G naught. So this thing we have seen. Okay. So what is appearing from here? My A naught is GM by G naught, which is nothing but GM R naught. What is my omega P1? From here, what we can see, omega P1 is nothing but G naught by CL, also called 1 upon R naught CL, which was 0 previously, now has some finite value greater than 0, because the output impedance of GM cell is considered. Okay, so what about P2 and what about Z frequency? Is these elements, is these components are available in op-amp, this GM cell or not, or are these available in 5T OTA or not? Are these available in 5T OTA or not? So this is the question. Okay, we'll come to this question when we'll enter at the design level or the transistor level. Before that, I'll enter to the phase margin and what is the influence of right hand side 0 on the phase margin. Okay, so I'll come to this second order transfer function. So order, we all know, two s components are there, s terms are there, so the denominator is the order of s square, so we can say the order of system is 2. Okay, so let we see the phase margin and what is the effect of right hand side 0 on the phase margin. Okay, yeah. So I think what we have covered in this video, so these are the things we have covered. Okay. So I think this is the fundamental things that we have discussed here. Oh, I think in next video we will discuss about the contribution of right hand side 0, and we'll discuss what are the things we will discuss in next video are phase margin is the main motivation, and second thing is right hand side 0 and effect of this particular on phase margin, and what is this means stability margins, where we will see from the Bode plot stability margins. So why PM means phase margin is important. We will see some sort of these things in next video. Okay, so these are few things more we'll discuss in coming video. Okay, so thank you for this video.